welcome to this lesson with teacher Kamanga. This is a science, specifically physics. We'll be looking at radioactivity. Now, this question was extracted from the past paper for GCE 2022, paper 1. This is section C, question 3. All right, so what we need to understand is that radioactivity is a very interesting topic, of which I encourage you to go through the notes, and you see that it is really an interesting topic. So I advise you to say after this lesson, please try to revise on your notes so that you're able to get one or two things from them. Okay, so the question is figure C3.1 shows a decay curve for iodine 131. Okay, we've seen the symbol there. Okay, so iodine 131, the symbol is I. Then we have the mass number of 131, then the proton number of 53. Okay, so the curve that we are seeing here, it is the one that we are calling the decay curve. So this graph is just showing us the decay curve. As we are seeing, the curve is moving in that direction. Okay, so I encourage you to say, as we are moving along, please try to get along as we are proceeding so that you're able to follow what you are supposed to do if you have been given such kind of a question. Okay, so when you look at this graph that we've been given, we have the mass here, and this is where the graph is starting from. So it is indicating that that is our original mass. So we need to know that. Okay, then as the curve is moving, it comes like that. Then it ends at 44. That is the time or the day. So we need to understand that this side we have the mass, and also this side we have the time. So what is really important to understand in this case is that we should be able to know to say what we are trying to to understand from the graph is that some of the many things that we expect to know what is a beta particle, to know what is an alpha particle, and also to know what is a Wille or a gamma radiation. So those are some of the things that we expect from here. Okay, so we understand to say when a radioactive element is unstable, it will try to emit some particles for it to be stable. So it will first emit an alpha particle. An alpha particle in nature, it is an helium atom. So we probably understand to say if it is an helium atom, the mass number of this alpha particle, it is 4, the proton number, it is 2, being the nature of the helium. So in most cases, as it is being emitted, we understand that the mass number of a radioactive element, if it has emitted an alpha particle, is going to decrease by 4, and also the proton number will decrease by 2. So that is just the nature of the alpha particle. So we need to understand that. Then also, if it is a beta particle that has been emitted, we understand to say in nature the beta particle, it is an electron. So we know an electron does not have a mass number, and also it has a proton number of -1. So basically what we need to understand, because there are some arithmetics there that we're supposed to do. So if a radioactive substance emits a beta particle, we understand that what will just change is the proton number, which is going to increase by 1. So that is very important that we need to understand. Now, if a radioactive substance emits those two, it is going to be left in an unstable state. So for it to be stable, it is going to emit an extra particle, which we call the Wille or the gamma ray. So now, this one does not change anything. So you're going to realize to say the parent particle, it is just going to be resemblance to the daughter particle. So the daughter particle will resemble to the parent. So there is no basically any change that is going to occur there. So those are some of the things that we need to understand as we are trying to review. Then also another thing that we need to understand is that probably maybe we might be able to talk about what we call the half-life. So the half-life of a sample, in most cases, it is just the time taken for half of the unstable nuclei to decay. So mostly we're talking about half. So it is going to be decaying half. So the time that is going to take for it to decay half, it is the one that we're calling the half-life. So we'll be having that understanding as we're trying to answer this question. So let's go back to our question and be able to answer. Okay, the first one is saying A1 is saying what was the original mass of the sample. So the original mass of the sample, like I've said, we just look at where the graph starts from. So we are seeing the 200 kg, that is the original sample. So we're seeing, say, 200 kg, that is the original sample. So 200 kg is the original sample in this case. So our answer there is going to be 200 kg as our original sample. Okay, that is very simple and straightforward. So the second question is saying, what is the half-life of the sample? What is the half-life of the sample? So since we're talking about the half-life, we're saying it's the time taken for the unstable radioactive element to decay half of its mass. So since the mass of, say, is 200, so what is the time it will take to decay half? So we're going to look at what is half of 200. It is 100. So we'll go where there is 100. You're on the mass side, so this side 100 there. So where there is 100, we're going to follow the line straight up to the graph. Then immediately when we meet the graph, we will come down. That's where we're going to find the answer. So we'll follow it from the 100. We'll go to the graph. Just make sure that you follow it straight, then you come down like that. Okay, so you come down like that. So this is where our answer is going to lie, where it is coming down. So basically, if you follow it nicely, you follow it just nicely, you're going to realize to say probably it is meeting it at the midpoint. So it will be just in between the 12. It will be just in between 12 and 8, in between 12 and 8, in between like that. So probably we're going to estimate to say the half-life in this case, it is 10 days, if you like. Okay, it is going to be 10 days. Okay, so because we have said 10, we're approximating to be in between 8 and 12. So if you follow it nicely, maybe you use a ruler, you are going to realize to say it's going to be in between the two, and it will be maybe 10 days. So the answer there, it's going to be 10 days. 10 days. Okay. Okay, I hope there we are clear. All right. We come to the third one. We're saying what quantity of the sample had remained after 24 days. After 24 days. We're looking at 24 days in this case. So we're going to follow, where is it, our 24 days? Our 24 days is just there down below. Okay, so we'll follow the 24 up to the graph. When it meets the graph, then we'll come direct to where the mass is. So we'll follow our 24 up to the graph like that. Then we'll follow it up to this direction. So again, we are going to use a ruler as we are trying to do this, very neatly, so that you'll be able to see where it will take you. So if we are trying to see where it is going to lead us, it probably maybe lead us somewhere there in between there. So we're approximating to say maybe our figure in this case, our answer in this case, it might be somewhere 19, 17, 18. So we can have a range. You are in this case, mostly when you are writing an exam, they mostly give an range in a situation like this, but you can still use a ruler to get an accurate answer. So if it is within a range, maybe you can put between maybe 16 to 19. An answer in between, it might contain decimals, it's okay. So for argument's sake, we're going to put 19. So we're going to put 19 as our answer there. So our answer is going to be 19 kg. So we can have a range, so maybe from 17 to 19. Yes, so any answer between 17 to 19, it will still qualify to be the correct answer. All right. Okay, I hope we're following. So we come to B, we're saying if the sample decayed by emitting gamma ray and an alpha particle to produce a new element X, write an equation for the decay. So we need to understand the sample that we've been given, it is the iodine. So the iodine, we said the symbol for iodine, it's 1, then we have 131, then we have 53. Now, since this, they have said it has emitted what we call a gamma radiation first. A gamma radiation, like what I've said, it is not going to change anything from this sample. So if it has emitted a gamma radiation, the daughter element will still remain like the same. So what we're going to do, proceed into the next element that has been produced, which is the alpha. So when the alpha has been emitted, we understand that the new element has been given the symbol which is X, like we can see there. So we're going to present it with X. Okay, so since it has emitted a helium element which is an alpha, so this one is going to reduce by 4, this one will reduce by 2. So if we the 131 reduces by 4, meaning that we're going to have 127 there, then down there we're going to have 51. Okay, so to indicate that what has been emitted is an alpha particle, we put plus H4 2. All right, so like that, meaning that what we're trying to say is that an element has emitted an alpha particle which has resulted into the delta one, as we are seeing in between like that. So we need to understand how we're supposed to do this. It's very, very important and very interesting. When you follow it nicely, you're going to realize that it is very, very simple for you to be able to follow it up. All right, let's proceed. We come to C. So this was our B. All right, we come to C. We're saying give two properties for each of. Number one, we have the gamma rays. So for the gamma rays, what we need to understand is number one, this one is unaffected when it is put in the electric or the magnetic field. So we need to understand it is unaffected when it is introduced to the magnetic field. Then also it has no mass. So that is very simple. You can still remember that. Okay, it has no mass. It is unaffected when put in the electromagnetic field. Okay, we come to C2. We have an alpha particle. So an alpha particle, we need to understand is that number one, it is positively charged. Yes, positively charged. Then the second one that we can still put, we can say it has high ionizing effect. High ionizing effect or high ionizing power. That's one and the same. If you want, again, you can still put it as a poor penetration power. So, high ionizing effect and also poor penetration power. So those are some of the properties that we need to understand for the alpha particle and also the gamma. So for the gamma, I've mentioned two. I've said it has no mass and also it is unaffected if you put to the magnetic field and also the electric field. For an alpha particle, I've said it has a charge of positive, it has high ionization power, and also it has poor penetration power. So that we need to get that one. We need to get that one. Okay. So for the mass, the alpha particle has the greatest mass amongst all. Okay, we come to D. We're saying mention one use of gamma rays. So the gamma rays, it is used in treating cancer. So we need to understand that. I will still mention another use. It is also used in sterilization of utensils. Those utensils they use in the hospital. So they sterilize them to reduce the spread of some maybe diseases, viruses. So they need to sterilize them. So we need to understand on that one. All right, so this has been Teacher Kamanga. Like always, try to go back to your notes, revise, go back to the questions so that you are able to have vast knowledge on this topic. If this is the first time you're watching this video, you can subscribe so that you do not miss any of the video that I've been posting, that I'll be posting soon. Okay, it has been with me, Teacher Kamanga. Prepare well for your exams.